はい。では、ベスト性能部門1位に輝き、経済産業省商務情報政策局長賞、エクストリームエッジ賞を受賞されましたチームユララさんに発表いただきます。プレゼンターはティンクガオさんです。プレゼンテーション自体は英語で行いますが、質問のある方は日本語でもいいので書き込んでいただくなりしていただければフォローをいたします。あと、多分発表内容とプレゼンが合ってないってちょっと Q&A も来てるんですが、距離的なところとかネットワークの話もあるかと思いますので、うまくご了承いただければと思っております。では、お願いします。
Good afternoon, everyone. Sorry, but I have to conduct this presentation in English. We are quite honored to be part of this context, and since we only have less than 10 minutes left, allow me to go straight into the topic. And we a team actually consists of 5 people graduated from same university. And first, this context is actually a straightforward objective detection task with more emphasis on implementation, since we conduct an early stage analysis before we embark on the real practical work. We've actually experienced the first AI edge context. What we learned from the first AI edge context is that the raw data doesn't change at all, and the lesson from last year is really useful. The leading board score over 0.6 could be easily achieved with fast RCN and the ResNet 50 backbone and the feature pyramid network. And thus we hypothesize that in this context, any detection network could achieve 0.15 goal easily. And as a result, the final roadmap to our solution is clear. First, we need to find the lowest possible resolution. And secondly, we need to find an easy to implement and lightweight model. And then we spend more time on hardware design, which is not really the field we are familiar with. And at last, we try to make few improvements as well as possible. And here we did a prioritization to improve the utilization of FPGA resources, as the other teams have done. And we also optimized the input resolution. Okay, let's go through them one by one. First thing is about the input resolution analysis. We conducted this with a strong model, and we draw a conclusion that 160 times 256 should be efficient enough to meet the 0.1 requirements, even taking into consideration the strong lightweight model gap and local leaderboard gap and the quantization error. Regarding the model, and the two requirements should be satisfied. First, it should be a standard model in order to avoid the compatibility issue. And second, it should be easy to implement to save time. So our choice is the mobile V2 backbone connected with feature pyramid network and using favor box strategy for bounding box regression and classification. The training and post-process strategy is also clear. We train our model on NVIDIA Tesla P100 GPU, and we divided the data into training and validation, and with 60 epochs, around 30 minutes should be consumed while training. And about the post-processing, we use the false conv-BN strategy to increase the speed of inference. And we also use the INT7 quantization strategy as the other team do. Well, hardware part is actually the most difficult part for us. We are not really familiar with that. So we went to the SIGNET FPGA seminar held in February in Yokohama. And thanks to the great speaker's instruction post, we could finally get DPU work. I think if he's here, we want to express our thanks to him. And until here, everything working well, and we could finally complete a summation, and we start to think what improvements we could make further. The first thing we could improve is that we found the time of reading of image resizing, and the post-process is almost equal to time of DPU inference. Thus, we made two threads to improve the utilization of and draw full power of the FPGA side. And here is the diagram of our strategy, of our working flow before we do the parallelization and after we conduct the parallelization. You can see that we, as one thread is doing the image resizing, the other, the DPU side, it says the FPGA side is doing the inference at the same time. Thus, we can save almost half of the time in total. And the second improvement is the optimization of our input resolution. As I said before, 160 and 256 is enough to satisfy the official requirement 0.15, but we want to improve the score we could get and guarantee we can get better score. So slightly increase the input resolution. Why we do that? We want to be safe and want to be more safer on the private leading board. And while we try to optimize the input resolution, we found that increasing the pixel horizontally, we could get more. We could benefit more than increasing the pixel vertically. This is because of the pedestrians could be detected more easier when you stretch the image horizontally. And here is the result we have during our test. And finally, this is the summary of our solution, submitted solution. Our model is described here. We use the 160 times 288 input size, and using the mobile V2 network connected with feature pyramid, and using the favor box objective for bounding box and the classification. Well, here is actually our local performance test. It's a little bit faster than the leading board, the public leading board score. I think this is because of the hardware difference. And yeah, actually we suffer a lot from the Ultra 92 V2 board. There are two testing samples of our detection. Well, I think this is our presentation. Thank you very much.
Thanks for this presentation. And do you have any comment? Okay, we have got two questions from the audience. And can you see the chat window? So question number one is for parameterization, how many DPU IP did you use when circuit design in the Vivado?
How many DPU IP?
So I think yeah.
We actually use, as you can see, there are DPU versions. We actually have no idea about the DPU before we start this computation. As you can see, in the final performance here, we actually have tried two DPU versions. These versions have been fixed with the number of DPU cores. If you check about the DNDK user guide, it will be written there.
So I think you might use the architecture of the B2304.
Yes, we use the B2304.
Yeah, that is the answer.
Yeah.
So second question is, if you use your original neural network that doesn't have the Xilinx tutorial, Do you customize C code for your network when quantization?
I think most of the other presenters has mentioned the procedure of applying a new network to the DPU. And the first thing you need to do, you need to get a cafe network, right? And when you get the cafe network, you need to use the VT's AI tools to compile. At first, they use the VAIQ, the quantization tool. And secondly, use the VIC, that is the compiling tool. And actually, I want to mention here that when you try to use the VIC compiling tool, there is the option inside it. It says that whether you compile your model in debugging mode or you compile your model in releasing mode. If you choose the releasing mode, that would be around 20% faster than the debugging mode. But the default is the debugging mode. So I'd like to say to the other team members, try, if you ignore this option, you can try when you after presentation. I think you will be surprised at the performance.
Okay.
Yes.
So please go ahead, sir. Kato sensei.
Hi, I'm a chairman for the steering committee of this competition. So thank you very much for participating in the context again. So I remember your team also joined the last competition. So hope you keep joining the competition in the future.
Thank you.
So I have a question. So you mentioned that you have your original network, but was it made completely from scratch, or did you reference some template network from somewhere in the world?
Actually, in this contest, we need to care about performance. So what the performance means is that we need higher FPS. So we need the network to be lightweight. And we also need this network to be standard, because when you try to deploy the network onto a FPGA board, if you use two original layers of deep learning network, that would be much more complicated. So you should use those standard one. When we designed this network, we took reference to the most of the standard component of the other detection network. For example, if you mention fast RCing, cascade RCing, they have the backbone, and they have the neck, and they have the B-box head. So we try to divide the network into several components, and we try to optimize each component. That is how our network
I see. So sorry, yeah, I think on the first slide, I think you show that you're somewhat based on fast RCNN. So that is, just let me make sure. So your network model, yes, because you made some modification, but it is with the basis of fast RCNN. Do you have any reason that other presenters, most of them tend to use YOLO v3 or YOLO v3 tiny? So you believe that a fast RCNN, well, from my point of view, in terms of the processing time, so YOLO v3 in original is quite competitive with fast RCNN. So do you have any reason that you choose fast RCNN as a base?
I know all the researchers and most of the reports has saying that YOLO v3 is the fastest network that could be applied to real-time detection. But actually, the speed the speed, the performance of the network is actually decided by the flops and the layers. You need to really evaluate the volume of a consumption of computation side. So your network is not really decided by the other people design. It's that you should design a network that costs less flops and costs less computation power. That could make your network more fast.
Okay, yeah, fair enough. Thank you. Yeah, congratulations again.
Thank you.
Okay, thank you. And I think your approach is quite different from the other guy because you have the experience of the first AI Edge contest. That is, I think, your goodness for this contest, right?
Yes, because the data is absolutely the same. So we know what the performance of the other network on this data set. So we could design our own network. Yeah.
So goodness, a good announcement is the first AI Edge contest also use the same data set of the first Edge contest of the semantic segmentation. So anyway, that's my something like that. Anyway, so okay, thank you for presentation and Q&A session. Thanks. では日本語に戻します。はい。では、以上で各部門6名のプレゼンテーションを終了します。参加者の皆様、改めまして、受賞者の方々に大きな拍手をお願いいたします。